All right, so I got exams posted on Friday. So one thing I think I had in the announcement was I kind of did like just a linear 5-point shift. It kind of got the average up to about what the other section was, so that they kind of making sure that, I'm lacking something in one section and not the other. It's kind of getting the average to be the same across the two. When I say the average, I mean the median. I'm kind of taking out some of the outliers. So after I did that, I identified your highest and lowest exam score. So remember, kind of they're weighted differently. So currently I'm treating your two exams as though they're going to be your best two, right? So I'll kind of say right away, usually final exams are a little bit better for most people. Obviously, I'm speaking about kind of the average here on the final than on the second exam. The second exam is usually one of the lower scores if I'm looking at just kind of the average across the class. So, right now it's treating those as though they're your two highest, but that could change depending on how you do on the final, right? Remember, the kind of your lowest exam is only going to be weighted 10%. So if you do better on the final, some of these get shifted around. You can improve your grade quite a bit, especially if you didn't do so hot in one of these exams. Right? So everyone's, highest exam, for not everybody, it was the first or the second. So it has specifically your highest exam and then your lowest exam weighted accordingly. I should get those third Excel. I got bogged down last week during office hours. It was giving a lot of exams across my different sections. I'm hoping to get those done. I might even work on them tonight, but hopefully, if I don't get them done tonight, they'll definitely be done tomorrow at some point during the day. Once those are done, kind of everything should be up to date on Canvas, and grades, kind of current grades should be reflected in that total grade, as you can see. Other than that, we'll kind of start on the last stuff, the last topics here today, kind of towards the final. We'll do some more hypothesis testing. We'll introduce a couple new topics. But like if you didn't understand the hypothesis testing and confidence interval portion too well, it's going to be important that you understand the mistakes that you made, because we're going to continue to kind of work on some even tougher examples with hypothesis testing and confidence intervals moving forward, at least in the first half of these topics we cover leading into the final. Okay. I will hand back the exams at the end of class today, help me learn their names even a little bit better, but also to kind of allow you to look at after class. I'll put up the exam as well as the answers, and this will allow you to kind of figure out which ones you got wrong and try to figure out, maybe rework and figure out where you went wrong or what you did wrong, so that when we get to the final and we have more hypothesis testing and confidence intervals, you can kind of improve how you perform in those. Okay. Any questions from me before we kind of get going here today on material? No? Okay. So I'll hand those exams back kind of at the end today. I'll leave some time. But before then, I put up kind of the new lecture slides for this week. There's also kind of move some of the data files around. We'll also look at Excel a little bit today. And we'll start out with what we had before was we were thinking about doing confidence intervals and hypothesis testing for where the true population mean or the true population proportion was. Okay. So although this is interesting and it allows us to understand something about hypothesis testing and confidence intervals, the more interesting kind of tests, hypothesis tests we're going to do are comparing two different populations, right? So we'll have confidence intervals and hypothesis tests for three different types of examples. One, we're going to be comparing the sample means for two different groups. I'll show you some examples that will motivate these. It might become a little bit more clear in a second. So we can compare the means when we know the population variances. We can compare two groups sample means when we only have sample variances. And we can also compare two groups proportions, right? There's a proportion of this group higher, lower, or something different than a proportion from another group, right? So this is a little bit more powerful. We can start to make some more interesting statements, as I think we'll probably see as we work through a few examples today. And we can do both hypothesis testing and confidence intervals for these same three different types of situations. Right? It can be very similar to what we did with one population, right? We had sample means with a known population variance, sample means with a sample variance, and then proportions. Well, now it's those same three. It's just we're comparing those between two groups. Okay? We'll also kind of touch on this slightly different idea, which is matched pairs, which honestly almost becomes a little bit easier than the other two population examples we have. but this won't be for a little bit of while. We'll probably work through this stuff this week and next Monday, and match pairs might come like immediately kind of following Thanksgiving, okay, or Thanksgiving break. So kind of the motivating examples to give you an idea about what this is going to look like. It's going to be something like we've got two different majors. So I think I chose econ theater majors here. We have their starting salaries, and we say, I can see these sample mean starting salaries from these two samples I took, one of econ majors, one of theater majors. I then want to say, okay, can I make statements about what's the true difference between econ and theater majors starting salaries? Right? So we don't know enough yet to know how to do this, but that's going to be what we're going to be able to answer, right? What's the true difference, or what are some values for the true difference between these two groups? Right? I've got some proportion example where we're thinking about maybe the survey results. So maybe it's how favorable people view a particular policy, right? Maybe we have a before and after time period, or I think here I did 2010 and then 2011. I could then compare what the views were of this policy across those 2 years. Did it become more favorable, less favorable, or is it any different at all? Right? The third kind of example would be something where we've got comparing the sample means of two groups. So here it was texters and non-texters, what their response time was while driving, but I only have sample variances. Okay, so I can build confidence intervals and do hypothesis testing for what the true difference is in response time for these two groups, texters and non-texters. It seems like a relevant, pretty real world application of this, or a real question we might have. Okay. So today we'll kind of primarily focus on just confidence intervals and hypothesis testing for the sample mean between two groups when we have known population variances. This isn't the most practical. Usually, if we don't have the population means, how the hell do we have the population variances? Well, we usually don't. We usually have sample variances, but we want to kind of have a starting off point, right? Walk before we can run. So we'll do it with known population variances first, and then switch over and see how do we do this when we only have sample variances. Okay. So what's going to be true is we've got two different populations or two different groups, right? So I'll phrase this in the context of our example, even though here up in the slides, it's kind of group one and group two, right? So for our first group, there will be some true population mean. We aren't able to observe it. We somehow are given the population variance for that group. We then take a sample, we can calculate a sample mean, and we'll have a certain sample size. We can then do the exact same thing for that second group, right? That group could potentially have a different population mean than our first group. They're likely going to have a different population variance. And when we take a sample, it could have a different sample size, and we're more than likely going to have a different sample mean. Okay. So I'm going to explain how we get to this. And I'm going to not use the board today. As we kind of get towards the end of the semester, I think I'm going to start doing more of the work on this dot cam. That way, in those videos, you have more of the work that I'm doing. So if you want to go back, kind of leading into the final to review things, you'll have me working through this. So, what we were thinking about was, if I think about the distribution of my sample means from group one, let me make this a little bigger here. If you can't see anything, make sure you actually know it might be a little bit smaller here. They should be normally distributed around whatever that true population mean is, right? I then can think about, maybe I've got I could do this all in the same color, I guess. I'm just looking at kind of an x-axis here. So if I'm thinking about, this is just some different values for the sample means. So here was the distribution of group one sample mean. Maybe group two's sample means are a little bit higher because the true population mean for group two is a little bit higher, right? And we know that the sample mean should be normally distributed around whatever that group's true population mean is, I should say. So if I'm thinking about this in my example was, well, that doesn't make sense in the context of the example. This would be like theater majors and kind of econ majors. So if the statistic that I'm actually interested in is what's the true difference between the population mean of these groups, all I can observe are sample means. So if I want to know what's the distribution of the sample means difference look like, or the difference between econ majors and theater majors starting salaries, well, the most likely difference for me to see is going to be, right, the most likely value I see for each group would be whatever has like the highest point right in the distribution. That represents it has the highest probability of occurring. So the most likely difference I see would be whatever this difference is. Okay? So let's say, I don't know, maybe this is 5,000. Right? And that is just going to be whatever that true difference in the two groups means are. From there, what are the next most likely outcomes I see? Well, these values are kind of the next most likely. So the next most likely difference that I see would be here, kind of values that are just above and just below that value of 5,000. Then what are the next most likely? Well, I can kind of see this wider difference, maybe slightly narrower, this really wide one. So you can kind of imagine what ends up being true is that the distribution for the difference in sample means, ends up being, as long as we have sample sizes over 30, right? Well, and the original data, we only need sample sizes over 30 if the original data we're sampling from isn't normally distributed. But our sample mean differences should be normally distributed around whatever the true difference is between these two groups, right? Well, if we've got a normal distribution, we can start to think about, well, I can do things like what we were doing before, confidence intervals, hypothesis testing. It's going to be a little bit more difficult because we've got a couple more moving parts now. We're not just looking at one sample mean, we're looking at the difference in sample means. But they should be centered around whatever that true difference is. And remember before, for any one group, the variance of their sample means was just the variance, and here, let's say this was econ majors, would be the variance of the data we sampled from divided by the sample size that we took. Okay. So it ends up being true about the variance for the difference in our sample means is that it's simply going to be the variance of the first group sample means plus the variance of the second. So here that would just be take the variance for econ major starting salaries divided by our sample size for econ majors and add to that the variance for theater major starting salaries. What am I doing? I'm looking at things before I'm writing them. And then divide by the sample size that we had for theater majors. Okay. So we're basically just taking the variance for each group's sample means and adding them together. That gives us the variance for the difference in those two group sample means. Okay. Now we don't have to like reconstruct this every time. If we're going to kind of keep this general, what that's really saying is the mean of the difference in my sample means, it'll just be centered around whatever the true difference is in those groups' population means. And then the standard deviation, well, I said the variance of the difference in sample means is just add the variance of each sample mean together. Well, if I want the standard deviation, I add those together then and take the square root, right? Taking the square root of the variance gives me the standard deviation. And that really, and kind of think about lines up with what I was doing here. It's just group 1 and group 2 were econ majors and then theater majors. Okay. So as long as I have this knowledge, I now have a different statistic that I'm looking at. The statistic is no longer the sample mean, it's the difference in two group sample means. But I know what they should be centered around, or I know the mean of the difference in sample means, and now I know the variance or the standard deviation of the difference in those sample means. So using that, I can start to create confidence intervals and hypothesis testing. Okay. So knowing this information here, let's try to construct what we think that confidence interval is going to look like. So with one group, we said take the sample mean, add and subtract a certain number of standard deviations. Well, this was the number of standard deviations the way we wanted to go. We then had to multiply that by whatever the standard deviation was on our sample means. But the equation that we had for that was just the square root of the variance from the data we sampled from over our sample size. Okay. Well, now we're interested in the difference in sample means. So we're going to center our confidence interval around whatever difference we find in our two group sample means. We'll sometimes refer to this as the sample difference, or kind of D hat. Right, the sample difference that we found, where the true difference would be just whatever that true difference was in the population means. Now, we usually can't observe this, right? The best guess we have about where the true difference is whatever sample difference we found. So we're then going to build a confidence interval around that so that we can, with 90 or 95 or 99% confidence, say the true difference falls somewhere in this range. So if we know the population variances of both groups, we can still use that standard normal distribution to determine how many standard deviations away we need to go to build our upper and lower bound. It's just now we need to multiply by the standard deviation of the statistic we're interested in. So now the standard deviation of the difference in sample means, which we just had on that previous slide, is the square root of each group's population variance over that group's sample size. And this should be the square root of everything here, and quite draw it low enough. So it's really following the same format, same principles apply. It's just we have a few more moving parts, right? But we're still going to look up that z value that gives us alpha over 2 on each side of the interval, the exact same way as what we were doing before, right? We're still centering our confidence interval around the statistic that we're interested in. And we're then multiplying that number of standard deviations by the standard deviation of the statistic we're interested in. It's just now we're interested in a different statistic. So we have a little bit different of an equation to use, okay? Any questions over any of this so far? We're just kind of establishing things here. So let's go back. There we go. So here's our confidence interval equation. We just kind of constructed that, just talking through it. And really at this point, right, we can kind of line that up with what we were doing before. So if I had a problem where I wanted to build a confidence interval, it's the exact same steps as what we had done with one population. It's just we have twice as many things, right? Double of everything, because we have two groups. So we now have two sample means, two sample sizes, and then two population variances. Our lower and upper bound equation becomes a little bit more complicated, but this guy here, we would still kind of think about, we're taking our sample statistic and then adding and subtracting our margin of error to get our lower and upper bounds. Okay. So let's try to work through an actual problem. We'll kind of go back to that econ theater starting salary data. Okay. So here, try to work, kind of take the information from the slides, jot it down here, and then we'll blow this up so we can see it a little bit better. Okay. So I've got my two groups, econ and theater majors. All right. So usually kind of the way that, however this is stated, difference between econ and theater, econ will be our group 1, and then theater majors will be our group 2 here. It ultimately doesn't matter which group we set kind of first in terms of the actual implications of our results, but on like a multiple choice, or if you're asked a question, kind of the first group that is stated you should treat as group 1, and then the second group treat as group 2. Okay. So here, if I think about what my confidence interval is going to be centered around, well, the starting salary I found for my econ majors was $45,000. So this was like the sample mean from my group 1. I'll then subtract the sample mean I found from group 2, which was what? 33,000 was the theater major starting salary. So my confidence interval should be centered around whatever this sample difference in means I found was, which looks like here should be centered around 12,000. Okay. Now from here, it's just a matter of, we know that standard deviation for the difference in sample means will be the square root of each group's variance, which we're given, each group's population variance, and then we're given the sample size of each group. So at that point, it's just a matter of plugging those values in. And I think the second group, theater majors, we had 6,000 as the variance, and we took a sample size of 50 for those theater majors. So all I'm doing is plugging in the information I was given here. So the only thing left that I have to do is find the z value for my 95% confidence interval. So if I want the z value for my 95% confidence interval, my alpha would be what? 95% confidence would be an alpha of 5%, or in decimal form, 0.05, right? Alpha is the percent outside my interval in decimal form. So if I want the 95% interval, 5% is outside of it. In decimal form, that's 0.05. The equation reminds me, yeah, but you have a side on each side of your confidence interval, or like a tail on each side. So you've got half of alpha, or here that would be 0.025. Right? So when I go to that standard normal table, I'm going to look up the area that I want in the tail, which is alpha divided by 2, or 0.025. Okay. So I'll go to my standard normal table, or my Z tables. I'm going to try to find the area I want in the tail. So I'm looking at the middle of that table. Looks like 0.025 is actually right here. So I go over negative 1.96. But remember, I've kind of got that positive and negative already built into my confidence interval equation. So even though I found negative 1.96, really I just need the absolute value of that, because I'll be subtracting 1.96 to get my lower bound, and I'll be adding 1.96 times the standard deviation to get my upper bound. Okay. At this point, I've got everything plugged in that equation. It's a matter of getting this entered into my calculator. Okay. Yeah.
So the numbers under does the 9,000 and the 6,000 need to be squared?
So if we go back to what we were given the population variance. So if you're given the variance, they don't need to be squared, right? If I only gave you the standard deviation here, then you would only have sigma, so you would have to square it. Yep. Yeah, it's a good thing to kind of look out for on those, right? If you have the standard deviation, you can't simply just plug the value in, because this is the variance. But if you know the standard deviation, to get the variance, you would just square that value. Any other questions on that one? Okay. So, at this point, well, before we go to the answers, I want to show you one more thing, because I showed you this before the last exam. What's another way I could have found that 1.96? I could have used my student T tables and just remembered that the very last row would give me the values I would find from the standard normal distribution. So I could have looked up, scroll up here, the area that I wanted, 0.025, but use the last row of that student T table. Sure enough, I get the exact same value of 1.96. Okay. So two different ways of doing that. I kind of think once we start looking up critical values and some other things, using that last row just kind of helps save a little bit of time, as long as we can remember that last row in the student T table represents the values we'd find from the standard normal distribution. Okay. So from there, all right, we identified all the information we were given. We started plugging in all of our values. We then realized, okay, I still need to look up that Z value that gives me alpha over 2 on each side of my confidence interval. Once I find that, I've got everything that I need to kind of plug in, and it's a matter of getting this entered in my calculator. So same as kind of with one population, especially with two populations, there's more moving parts. I think working backwards helps prevent making any order of operations mistakes. So, another way of doing that, calculate this first. That way you only have to take whatever number this is, multiply it by 1.96, and then add that to whatever your sample difference is. Just breaking it down into parts just always helps kind of prevent making some mistakes. But if we were to do this here, we end up with a pretty tight confidence interval, right? Pretty narrow range of values, right? So what this would kind of represent is that with 95% certainty, I can say that the true difference between these two groups, right? The true difference between econ and theater major starting salaries is somewhere in between 11,960 and 12,000 about 40. Okay. Now, one thing that's interesting when we start looking at the difference between two groups is, notice this only contains positive values. Okay. So if it only contains positive values, what that's really saying is that, think about this. So I've got, I'm saying that true difference, right, which would be econ minus theater major starting salaries, with 95% certainty, I was saying that it's some positive value, right? The only values in that range are positive. So if I rearrange this a little bit and I add the population mean for theater majors to both sides, if this difference is positive, what I'm really saying is that with 95% certainty that econ majors are making more than theater majors, right? Because the only way this difference is positive is if this mean is higher, right? So if I ever have only positive values or only negative values, I can start to make some really interesting statements here about the difference between the two groups. Now, what if instead, it doesn't really necessarily match up with our findings, but let's say we had some different values from our sample means, and we found, I don't know, something like this, right? So we build the confidence interval for the difference between econ and theater major starting salaries, and this is the lower and upper bound I get. Okay. At the 95% level, then, what can I say about the relationship between econ and theater major starting salaries here? So that difference, right? Remember, my confidence interval is for what that true difference is. So that true difference could be positive, which would imply econ major starting salaries are greater than theater majors. But remember, with 95% certainty, I'm saying the true difference is any one of these values. So the true difference could be negative, which would imply theater majors have a higher starting salary than econ majors. And one of the true values for the difference could actually be here 0, which would imply what? That the starting salary is the same. So anytime I have a confidence interval that like crosses over 0, I really can't say a whole lot, right? With whatever level of confidence that is. Now, if they only included positive values, that's where I could say, okay, with that level of confidence, I can say that group 1 or the econ majors here have a higher starting salary. And I could do this with any majors that I wanted to. I could start to compare their starting salaries based off some samples and construct these different confidence intervals. And for maybe some of them, I could say one makes higher than the other. For some of them, I'll have this confidence interval that crosses over 0, and I can't really say much. Okay. So this is kind of the usefulness of these confidence intervals, right? If they're only kind of positive or negative values, that's where I'm able to start to say some pretty interesting things. Excuse me. Any questions on this before we keep moving? All right, so here we are. So let's say I had a slightly different example. What do I want to do here for the sake of time? So let's say that I had Indiana and Ohio robbery rates, right? And I'm going to I have the same time period for both of them. So it's like I have the same sample size. Okay. So in Indiana, I found the mean robbery rate to be 109. For Ohio, I found it to be 163. Right? I then have the given population variance for both of these groups. And I want to build a 95% confidence interval for the difference between Indiana and Ohio. I'm going to give you guys a softball one here. So if I'm looking at these values, right, respond here fairly quickly. Remember, the sample mean in Indiana was 109. The sample mean in Ohio is 163. If I want to build the 95% confidence interval for the true difference between Indiana and Ohio, which of these confidence intervals could I rule out right away? Right? So you don't have to work through this one, right? I just want you to choose the confidence interval that you could rule out right away based off of just the sample means that you found. Remember, what do I want here? Where's my, oh, hold on. The recording's going to be a little bit weird there. So I accidentally had it on the screen. All right. So, right. Remember what we're doing, kind of building these confidence intervals. So I'll leave this up here. Which one of these confidence intervals can you rule out right away just looking at the difference in the sample means that you found? Right, so I'll give you about 30 seconds here. So I don't have this label as an iClicker, but I'm using this as an iClicker question right here, right? So make sure you're getting an answer in. I'm going to close this out. So does everybody make sure they got a registered answer for which one of these confidence intervals can you rule out based off the sample means that you found? So we've got 22 of us, 23. Everybody got an answer in? All right, we'll close it out. So which one can I rule out right away? Why?
It has to be a negative answer because the robbery rate is lower in Indiana than in Ohio.
Yeah, right. So think about what I'm trying to do is build the true difference. Sorry, the true difference between these two populations. So I've got Indiana and Ohio. So my confidence interval will be based around whatever sample difference I found. So I had what, 109 for Indiana minus 163 for Ohio. So my confidence interval should be centered around negative 54, right? If negative 54 is what my confidence interval is centered around, then how could my confidence interval only be positive values that wouldn't even include the sample evidence that I found, right? So one way to rule some things out pretty quickly, like when it comes to the exam or something, is just think about the sample difference you found. It's a little bit different than what we're doing with one population because you could see the sample mean that your confidence interval is centered around. Now you can't directly see it, right? Because you're given the two sample means, and really what you're building your confidence interval around is the sample difference, right? The difference in those sample means. So sometimes it might be useful to, okay, figure out what that sample difference is and then just write that number down so that you can kind of think about, this is the value that has to be smack dab in the middle of my confidence interval, okay? Any questions on that one? Now from there, it's just a matter of using that equation we have for the confidence interval. We have the population variances for both groups. We've got the sample sizes, which was just 24 years for both because we had 24 years of data from each one. And then that Z value should be what? Well, we did the 95% confidence interval in the previous problem. So if I know the population variances, I'm using that standard normal distribution, the 95% confidence interval, I'm going to look up the same alpha value divided by 2. I should get that same Z value of, oh, there it is. Yeah, 1.96, right? So then I had everything, I would have everything I need, all right? It's just a matter of plugging everything in, computing it, and in my calculator to get the lower and upper bound, okay? So here, what could I say with 95% confidence? Remember, this is like the average robbery rates in both states. With 95% confidence, I could say what here? Yeah, right. If it's only negative values, that means the true difference is somewhere in this range. So the true difference, Indiana minus Ohio, has to be negative, which, right? If I go back and look at this, to kind of help us visualize it maybe. If this is negative, the only way this is negative is if Ohio has higher robbery rates, or said differently, Indiana has lower robbery rates. Okay. So this is kind of how we'll start to be able to interpret these confidence intervals when we have two populations and we're comparing their means. Okay. Any questions on that one before we keep moving? So when it comes to hypothesis testing, we've got a slightly different way of thinking about it for two population examples, but really there's only going to be one difference between doing hypothesis testing for one population and now comparing the means. Okay, so we're going to call that true difference capital D, right? When I was thinking about that, true difference was just the difference in the group's population means. Okay. We're going to have some assumed true difference for that value. Usually it's 0. In fact, for the sake of this class, anything I give you, I'll always be using the assumed true difference of 0. Okay. We'll see how that makes life a little bit easier here in just a second. So we're going to have the same 3 types of tests as we did before. We're going to have an alternative hypothesis where I say, assume the true difference, not assume, sorry, where I'm testing for whether or not the true difference is greater than 0, less than 0, or not equal to 0. So same one-sided and two-sided hypothesis tests, right? Left, right, and two-tailed. Nothing here changes at all other than the notation. Instead of looking at a mean, we're looking at the true difference in means, right? And it actually comes a little bit easier because I'm always going to assume that that true difference is either greater than, less than, or equal to 0 here, right? So that makes it a little bit easier. And we'll kind of see why in just a second. Okay. When it comes to the steps, everything's exactly the same. These are the same steps that we had before to do critical value, or we could have the same steps to do the p-value approach. The only difference is how we're going to calculate this test statistic. Okay. So let's see if we can kind of piece this together before I even show it to you. Right? When we had one population examples, to find that z statistic or that test statistic for a sample mean, I subtracted the assumed true mean, and I then divided by the square root of the population variance of the data I sampled from over the sample size, which really all this represented was the standard deviation of my sample means. Okay. So when I'm wanting to do a test statistic for the difference in sample means, well, I want to keep this on. Actually, I don't need to show you that right now. So let's see, I want to make sure I can get this all on the screen here. If I'm thinking about the distribution of my difference in sample means, they should be centered around whatever that assumed true difference is. I told you I'm always going to assume that it's either less than, greater than, or equal to 0. So that assumed true difference value will always use 0. Okay. And we said that the standard deviation for that difference will be the square root of each group's variance over that group's sample size, kind of add it together. And then we want the standard deviation, so we had to take the square root. So when I want to find this test statistic, it's the same setup. I take the statistic I'm interested in. So instead of the sample mean, now I'm interested in the difference in sample means, right? Or we said kind of the sample difference. I'll subtract the assumed true value of the statistic I'm looking at. So here that would be the assumed true difference, which I said will always be 0. So we can kind of ignore this, right? Subtracting 0 isn't going to change anything at all. So that's when I said, it almost makes it a little bit easier than what we were doing before. And then I'll divide by the standard deviation of the statistic I'm interested in, which is now the standard deviation of the difference in sample means, which we have already used for the confidence interval. So it's just going to look something like this. Okay. So we're really following the same procedure we did before to calculate the test statistic. It's just, the standard deviation now is a slightly different, more complicated formula. And like the assumed true value of our test statistic, I'm going to simplify with always using that value of 0. Okay. Any questions here? So one thing that becomes a little bit easier with these two population examples, if I always have this assumed true difference of 0, let's say I look at my sample means and the difference is positive. What's going to be true about my test statistic? If the sample difference, or the difference in sample means that I find, is a positive value, when I turn that into a z statistic, a test statistic from a standard normal distribution, that's telling me the number of standard deviations away from that assumed true difference. Well, if I see a positive value, that's going to be a certain number of standard deviations above the assumed true difference. So if I see a sample difference that's positive, my test statistic's positive. If I see a sample difference that's negative, I'm going to be a certain number of standard deviations below the assumed true value. So my test statistic will be negative. So whatever the sample difference I find is, that tells me the sign of my test statistic in these two population examples. Another reason to kind of identify why that's the case, notice what's in my denominator. It's a standard deviation. That will always be positive. All right, we can't have a negative variance or a negative standard deviation. So whatever the sample difference I find is, that automatically tells me the sign of my test statistic. Okay. And that's only because I'm using the assumed true difference of 0, but because I'm doing that for you, it makes it a little bit easier. Okay. And I'll show you what happens if we don't use 0 there, probably in some, once we get to Excel and work through a couple examples there. But for now, you can kind of just know that we're always going to use 0 here. Okay. So if we go back, right, same steps. The only difference is our test statistic equation has changed a little bit. So when it comes to p-values, this is the exact same slide I showed you before. Everything's exactly the same. For a right-tailed test, we want the area to the right of the test statistic, left-tailed area to the left. Two-tailed test, we find the area in one of the tails and then have to multiply it by 2, right? Looking up the critical values, we're actually going to find the exact same values we did before, because the critical values were just the values from the Z, or the standard normal distribution, that gave us the desired alpha over 2 in each tail. And we're going to keep comparing to the same 3 alpha values that correspond to the 10, 5, and 1% significance levels. Okay? So nothing's changed here. Like, we'll draw out our rejection regions and kind of see if our test statistic is in the rejection region or larger in absolute value than the critical value. If our test statistic is larger in absolute value than our critical value, we can reject. If it's not, we say we failed to reject. So all the same rules and principles apply as what we were doing before. The only difference is we have a new equation for our test statistic. Okay? Any questions on this one? Anything here before we kind of move through and work through an example?
So the D is always going to stay constant.
Yep, I'm always going to use the assumed true difference of 0. I think we'll have just enough time today where I'll walk through an Excel example and I'll kind of play around with it at the end to show you, well, what if you didn't want to test against 0? But for the sake of any problem I gave you on the exam or even on the homeworks, I've made sure that I'm using that value of 0. All right, so let's work through a problem. So let's say I've got some data on tropical storms, right? And I want to know, have tropical storms in the Atlantic specifically, have they increased in recent years? So I've got a more recent time period, which has 22 years of data. So my sample size there is 22 years, so 22. Got some older time, an older time period, my older years, I've got 32 years. So my sample size from that older time period is 32. I've got the sample mean for the average number of storms I see every year in both of these time periods. And for right now, we'll assume somehow I was given these known population variances. Okay. So if I wanted to figure out whether or not tropical storms have increased, right? Well, first of all, I just told you that for this assumed true difference, I'm always going to use the value of 0. So here, we should automatically know it's going to be C. Right? But let's say I gave you some more realistic other options. Why do I know it's C? Okay. Well, if I'm thinking about, have tropical storms increased, right? The difference I'm thinking about, and I'll just use the end here from both ones to identify the group. So here was my newer time period minus that older time period. If tropical storms have increased, what would have to be true about this difference? If they've increased, it would have to be positive. I said that's what I wanted to test for. So that's my alternative. I'll then assume the opposite is true, which is that that difference is less than or equal to 0. Now, I'm writing it out here. If that helps, write out what your difference is, right? The shorthand is this is just the true difference, right, between the newer and older time period. But if it helps to write it out for you to think about what you're testing for, right, is this difference greater than 0? When I write this out and kind of see, oh yeah, the reason why I want to know is it greater than 0, because that would imply that it's increased, right? There's more storms in the recent years than the older years. Or if I think about it this way, if I want to know, have the tropical storms increased? Actually, let me do it this way. I'd say, okay, if they've increased, that means it's higher in recent years and older years. Now I'm just going to use a little bit of algebra so that I can write this out as the difference between the two. Subtract the mean from the older time period from both sides. I would end up with this. This represents my difference. So I'm really just saying I want to test for whether or not that difference is greater than 0. It's a little bit trickier to identify normal alternative hypothesis with two population, I would say. But the one thing with time periods, always think about when I'm thinking about this difference, my newer time period should be first, right? That lines up with the way that we speak in English, right? Because then I say if storms have increased, then my difference is positive. if I turn it the other way around, then actually, you know, if I say that my difference is this, then when I'm saying have storms increased, I would actually find like a negative difference here, which doesn't really line up with the way that we say it in English. So anytime we're looking at like comparing an old to a new time period, always put your new time period first and the older time period second, right? And that's just typically lines up with intuitively how we think about the difference between kind of crossing across time periods, right? Okay, so what type of tailed test do I have here? What sign? Yeah, so I've got a greater than sign of my alternative hypothesis. So I've got a greater than or a right-tailed test. Okay. So if I look at the sample difference that I found, what's the difference in my sample means here? It's what? 5.8. So I found a positive sample difference. I have a right-tailed test. So if I'm thinking about the distribution of this difference in sample means, it should be centered around this true difference of 0, if it in fact is the true difference, right? That's the value that we have in our normal alternative hypothesis. I found a sample difference of 5.8. Okay. So if I then think about, I'll skip this for a second. If I wanted to calculate my test statistic, right away I know my test statistic has to be what? Positive, because I found something that's a certain number of standard deviations above that assumed true difference, right? Now, I can't say much more than that, right? And from here, right, I want to convert that sample difference value into a test statistic or into a Z statistic, since I know the population variances. So I know it'll be coming from a standard normal distribution. Okay. Now from there, oops, it's just a matter of plugging my values into that test statistic equation, right? Once I have that in front of me, I was given the two sample means for both groups, given the population variances, and given the sample sizes. Now that assumed true difference of 0, I can ignore that if I want to, because subtracting 0 doesn't really change anything. But at this point, it's just taking that test statistic equation. We're given all the information that we needed. You can plug everything in here. Okay. Any questions on this? Yeah.
Just in the bottom of the denominator.
Yep.
9.7 that was inserted.
Oh, it should be 7.8, shouldn't it? Yep. When I post the complete version of the slides, I'll have this saved in there. So let me save this actually real quick so I don't. There we go. Yeah, so if we look back at the original information, sorry about that, good catch, right? The variance from that second group was 7.8, not 9.7. But really, it's just a matter of plugging our known values into that equation, okay? Any other questions on this one? So we just found what, 4.9? So for a right-tailed test, if I wanted to look up my p-value, that would be the area to the right of my test statistic, or the probability I saw the test statistic I did, or anything more extreme. So for a right-tailed test, that's the area to the right. For a left-tailed test, that would be the area to the left. For a two-tailed test, right, it kind of depends on what the sign of my test statistic is, but I'm just looking kind of into the tail there, and then whatever area I found in the tail for a two-tailed test, I would take that and multiply it by 2. Because evidence on the other side would have been equally as likely for me to see and would have won against the null if I had a two-tailed test. But I don't have a two-tailed test. I just have a right-tailed test here. So once I find that area in the right tail, that would represent my p-value. So how can I find that? Well, if my test statistic comes from that standard normal distribution, I can go to that Z table, look up 4.9. Now the table will tell me the area to the left. So if I want the area to the right, what's the other step I'll have to do? If I know the area to the left of 4.9, how am I going to find the area to the right? Yeah, just 1 minus whatever this value is. So I try to look up 4.9. I'm going to have a problem because my table only goes up to 3.99. But if the area to the left of 3.99 is basically 1, then the area to the left of 4.9 should be even closer to 1, right? So really the table just told me the area to the left of 3.99, that this area is approximately 1. So adding in this area, I'm going to be even closer to being approximately 1, right? Which means the area on the right is going to be approximately what? Yeah, 1 minus approximately 1 is going to be approximately 0. So what levels can I reject at here? Yeah, so if we recall, our rejection decision is if that p-value or the probability of seeing something as far away from that assumed true difference as we did, right, or anything further, that probability is less than our threshold alpha we set, then we're okay rejecting. Well, here, the probability being approximately 0, that's going to be less than 0.1, 0.05, and 0.01, so we can reject it all. Right? Okay. Think about it. I mean, being 5 standard deviations away from the assumed true difference, that's very unlikely. So what we're really saying is we're rejecting this assumed true difference because based off seeing the sample difference as large as we did, it's probably more likely the distribution of our difference in sample means is probably centered around a much higher true difference, right? Something like, I don't know, 4 or 5, I don't know what it would be, right? But something above 0, right? So we're saying this doesn't make any sense. This assumed true value of 0 makes no sense based off of the sample evidence we found. Okay. Any questions on that? We keep moving here. Okay with this, at least for now. All right, so looks like we're pretty good on time here. I want to show you how we do this in Excel. So let me minimize this. Let me open that to population HT blank. So this is up under the in-class data folder. We're going to start on this Midwest file. Okay. So we've done, I kind of show you how to do some of the confidence intervals and hypothesis testing stuff with one population, but we'll really kind of hone in here for the 2 population stuff. So I've got this Midwest data file, which has a collection of universities that are D1 universities in the Midwest. I then kind of have what their total undergraduate enrollment is. So I'm going to try to find the mean undergraduate enrollment at these Midwest universities. All I'm going to do is use that average function, right? Finds the sample mean, select all of those universities undergraduates. And I've got about 14,000 as a sample mean undergraduate enrollment. I've given you a known population variance. Once again, this is kind of a goofy example, but this would have to be something that would have to be given to you, right? If I then want to find my sample size, I use that count function. I've now got my sample mean, my sample size, and a known population variance for my first group, which is the Midwest, okay? I'm then going to go over to this South worksheet. I've got the same kind of data, but now it's for schools in the South. And I don't know, maybe you want to argue that South Carolina or something is in the South, but for the sake of, this example, like whatever states I chose here, we're going to classify as universities being in the South. So here, I'm going to find the sample mean for total undergraduates in these Southern schools. So Control Shift or Command Shift on a Mac, hit the down arrow, then hit Enter. I gave you a known population variance for the Southern schools. We could then find this sample size for my Southern schools by using that count function. And now this is where I haven't shown you how to do this yet, but it's really easy, right? So my Midwest data was on a separate sheet, right? If they were all both on the same sheet, maybe this would be a little easier, but it's not. So one thing you can do is actually cross-reference sheets in Excel. So for any of you accounting majors, whenever you're doing like all the stuff I forgot, like balance sheets and all that junk, right? Well, I shouldn't call it junk, right? I guess it is important, but right, there's a lot of things that are going to be on both those sheets that you want to like cross-reference, right? So here, I want to put the Midwest sample mean in. If I put an equal sign, then I select this sheet and select the sample mean. Notice up here in the formula bar, it's basically telling Excel, go to the Midwest sheet and put the value that's in cell M4. So after I select on that, if I hit enter, it sends me back to the worksheet I was on. And notice it's got this kind of nice cell reference that's referencing another worksheet for me. All right. So that kind of makes, like I said, in accounting, this is like really valuable because you can put everything in the same Excel workbook, and then you can just like reference these things across your different documents that you want to be looking at. Okay. I also can do, right, my sample size was over there as well. So I click on that, hit enter. Now I've got the sample means, the known population variances, and the sample sizes for both groups on the same worksheet. Okay. So the next thing I'm going to do is use Excel to construct my confidence intervals for the difference between Midwest and Southern schools' average enrollments. Okay. So the way that I'm going to set this up is, move this out of the way first. I'm thinking about, I want to construct a confidence interval for the true difference in Midwest and Southern enrollments. Right? So basically, I'm going to write this out in the context of my example, just in the general form. And kind of have this up here as we work in Excel. Okay. So there we go. So the first thing, I've got all the information I need here. So I'm basically just going to use Excel as a calculator to do this. Okay. So the only thing I really need to use Excel for here now is to find these Z values. Now I could look them up by hand, but I can be a lot more precise and exact in Excel. I know the area that I want in the tail, alpha over 2. So I'm working in reverse, right? Or I'm using that norm.s.inv function. I'm going to tell it the area I want in the tail, or that probability, which is just alpha divided by 2. So I take alpha divided by 2. Now the problem is going to be when I find the Z value, just like on the table, it's going to tell me the number of standard deviations I need to go below to get my lower bound. But I don't really want to have the sign here. I just want to know the number of standard deviations above and below I need to go. So if I hit enter here, notice it gives me a negative value. Well, I just want the absolute value of that when I'm using it to calculate that lower and upper bound, right? Because that positive and negative sign is already built into my upper and lower bound equation, right? So if I hit enter here, to get my lower bound, well, first of all, I could just copy this down. And it's going to update that alpha reference so that I get the number of standard deviations away I need to go, or that Z value for my 3 different confidence intervals pretty quickly. Okay. From there, I'm going to do the lower bound, which I'm going to break this down into parts. It's going to make my life a little bit easier kind of in the future when I do some hypothesis testing as well. So notice here, what this represented was the standard deviation for the difference in my sample means. So I'm just going to put that in a cell right here. Okay. And actually, I had this problem in the last class, so I want you to be able to see this. So you don't have to move this, but I think so you can see everything. I'm going to move it down one. Oh, come on. There we go. I'm just going to move this down one so that, okay, I don't really care. So that you can kind of see what I'm doing. So I'm going to put, this is just the square root of that first group's population variance divided by the sample size. Add to that the second group's population variance divided by its sample size. Okay. So just using Excel to be a calculator here, and I'm going to kind of do this in steps so I can have this value in a different cell. Okay. Questions on that? We keep moving here. All right. So from here, my lower bound equation is just going to be take the Midwest sample mean I found, subtract the Southern sample mean that I found. and then subtract to get my lower bound 1.64 standard deviations times whatever that standard deviation was for the difference in my sample means. Okay. So if I break this down into parts, it makes it a little bit easier in Excel. And then if I want to copy this down to get the lower bound for the next two confidence levels, what am I going to have to do before I copy this down? The only thing I really want to change is that number of standard deviations away that I'm going, right? My sample sizes, my sample means, my variances, they haven't changed at all. So that's the only thing I'm not going to freeze is that Z value. So I go up here, Command T or F4 on a PC. Command T was on the Mac, sorry. I want to freeze everything that's not that Z value. Okay. Now when I copy this down, I get my lower bound, and these references haven't changed, but it's updated the number of standard deviations that Z value. That gives me alpha over 2 in the tail, because alpha is different for my different levels of confidence here. Okay. Any questions on that before we keep moving here? All right, so then to get my upper bound, because I showed you how to do this with one population. Remember kind of a nice, easy shortcut I told you here. Double click on that cell, highlight it, copy it. If you hit enter, it just takes you out of the cell right away. Go over here and paste it. The only thing, when you do it that way, none of the cell references change. And then instead of subtracting that margin of error to get your lower bound, you're just adding the margin of error to get your upper bound. Okay. Hit enter. Now I can copy this down. And now I've got 3 confidence intervals pretty quickly. Okay. So what is this really saying here, right? I've got this confidence interval for the true difference in the means between Midwest and Southern schools, and it goes from, and I'll blow this up in just a second, 54 to 7,761. Okay. So really what this is saying is that the true difference is a positive value, or that with this was the 99% level. So even at 99% level, I can say that Midwest schools have a larger average undergraduate enrollment than Southern schools, right? Or that the average size of a Midwestern school is bigger than a Southern school. Any questions on this here? Okay. All right, so we got one more thing that we'll kind of work through. And I have to change this because I was doing this for the other section earlier today. So I'll put a 0 in here because I told you I'm only going to use assume true differences of 0. But I'm not going to show you what we could do if it wasn't 0, kind of for things outside of this class. So really, when we're doing hypothesis testing in Excel, to calculate this test statistic, it's simply going to be using Excel to be a calculator, right? There's no built-in function, there's no built-in formula, just to find that test statistic. Okay. So here, I'm going to go back to, I had it written down somewhere, basically entering this equation into Excel. But notice, the denominator of my test statistic equation was that standard deviation of the difference in my sample means, which I had broken down into parts and had already found for the confidence interval. So the test statistic is really just take the Midwest sample mean, subtract the Southern school sample mean, subtract that assumed true, assumed true difference of 0. Now, it might seem like, why am I doing that? In practice, you don't have to, right? Subtracting 0 isn't going to change anything. But I'm in a second going to show you what happens if it's not 0. So that's why I'm including it. And then you divide it by that standard deviation of the difference in your sample means, but we already found that for the confidence intervals up here. So we can kind of double dip with that, right? We can use that twice. That way I don't have to type out all of this, right? No, I could, right? But since I've already broken it down in steps, I might as well use the work I've already done. Is that clear why I can do that? Because that was the exact same thing that we had over here in my confidence interval. I've got group 1 and 2 here, but group 1 was Midwest, group 2 was the South. So I've got what type of tailed test here, kind of similar to the example we did in class already. Got a right tail test. Okay. So just like I looked it up in the table, I would look up 2.6. However, it's a right tail test, so I want the area to the right of it. Well, if I use the built-in norm.s.dist, right? So I'm not working in inverse now because I'm not looking up the area in the tail. I'm looking up the actual z value. I want to know the area to the right of 2.6, but this function, if I select the z value and then comma 1, always gives me the area to the left. Now, I said this before, kind of looking at some of the Excel assignments. I think maybe people either forgot or kind of were confused. Putting a 0 in here does not give me the area to the right, right? Putting a 0 in here like breaks it down to 1 unit and gives you the probability of being in between your z value and like 1 away, which I don't understand why that's very useful in a lot of these examples. So I don't even know why it's an option. So we always use that comma 1, and it's always going to act just like we were looking up this up in the table. It's going to give us the area to the left, but we wanted the area to the right. So we're going to have to do what? Yeah, simply subtract it from 1. Right? So this should give me my p-value. Okay. From here, right, I could find my critical values, right? But I'll hold off on this for a second and show you kind of a nice little shortcut or kind of a neat thing you can do in Excel that we haven't looked at yet, or at least I haven't expected you to know how to do yet, okay? Which is this if statement. So what the if statement is going to do is it's going to check to see if something's true. If that thing is true, you're going to tell it what you want Excel to put in the cell. If that thing isn't true, the third thing you'll tell it is what to put in the cell if that was false, right? So I'm going to check to see, okay, is my p-value less than alpha? That's my rejection decision, right? If the p-value is less than alpha, I say I reject. So if that p-value is less than alpha, comma, put in the word reject into this cell, because I should be rejecting. Right? Now, I have to put any word that I want displayed in a cell in quotation marks here. So that's why I have kind of reject in quotation marks. And then comma, if this is false, if the p-value isn't less than alpha, well, that means I should be failing to reject. So put in the word or words, fail to reject. Right? Now this will kind of automatically, now if I look at this, for a p-value of 0.004, what levels here should I be rejecting at? Well, that p-value is less than 0.1. Is it less than 0.05? Yeah. Is it less than 0.01? Yeah. So just eyeballing it, I should reject at every single level. Okay. Now I've done the rejection decision at the 90% level. If I wanted to copy this down, what's going to be something I need to do? At different levels, I want to compare to different alpha values, but I'm always using the same p-value. So I'm going to freeze that cell reference. Now, if I copy this down, I get my rejection decision at all 3 levels. Notice it's updated the alpha it's comparing to. But here I had a p-value where I would reject at all levels, right? Just eyeballing, I could see that. And sure enough, using that little built-in if statement kind of allows me to see that as well. Okay. Any questions over that before we keep moving here? So we got 2 more things I want to show you. So the first is, how would I find my critical values? Okay. So critical values are just the z values that give us the desired alpha in our tail. Well, we're looking at a right tail test, right? So if I'm thinking about, if I want the critical value that gives me, let's say, 0.1 in that upper right tail. If we use the inverse, that norm.s inverse function, or INV, I need to tell it the area to the left. So if I have a right tail test, I can't tell it 0.1 because I need to tell it the area to the left. So what I actually need to tell it would be, right here, 0.1 was alpha. So I'd actually need to tell Excel 1 minus alpha, right? Because it needs to know the area that I want to the left of my critical value. Well, I know the area I want to the right is alpha, so the area to the left must be 1 minus alpha. Okay. So when I go to Excel and I use that norm.s.inv, very similar to, that's the function I was using to look up that z value for confidence intervals. But now I know the area to the left I want is 1 minus alpha. Right? And that should give me positive critical values for my right-tailed test. Right? Sure enough, 1.28. I can copy this down, and I've got my 3 critical values fairly quickly here. Okay. Now, when do we reject with the critical value approach? Well, that's just if the test statistic is more extreme or greater in magnitude than my critical values, which sure enough here, 2.6 is greater than all of these. So it should lead me to those same rejection decisions as the p-value approach. Okay. Anything else? Any questions here over anything that I've done up to this point? Okay. So we got one final thing I'll show you, but I won't expect you to ever do it. Right? So here, what can I say at the 99% level even? Well, if I think about, I can reject that this difference is less than or equal to 0. So basically, I can reject that Southern schools have a larger enrollment. Right? I found very strong evidence that goes against this null, which is that the true difference is greater than 0. Right? That's the evidence that I found that goes against the assumed value that it's less than or equal to 0. So if I'm rejecting that the difference is less than 0, what I'm really saying is, oh, where did I have it before? I can reject that. If this, I'm rejecting that this is negative. I'm rejecting that the Southern schools would have larger enrollments. And that kind of makes sense. I found pretty strong evidence that Midwest schools have a much higher enrollment than the Southern schools. But can I reject, say, that, can I say that Midwest schools have more than 1,000 additional students compared to a Southern school? Well, if I want to do something like that, my assumed true difference isn't 0. It would actually be 1,000, right? So I could change my null alternative. Maybe if I can get this selected correctly here. There we go. I could change that to 1,000. Everything will automatically update. And now see at the 99% level, I can't actually reject that kind of Southern schools have at least, 1,000 or fewer students, right? Just barely. I'm, 0.025. So I just barely failed to reject that 99% level. Okay. So I could play around with different values. I'm just not going to expect you guys to ever do anything with any examples we use in class. And honestly, more often than not, we don't say things like, well, do the Midwest schools have more than 1,000? We usually just say, do they have a higher enrollment? Do they have a lower enrollment? Is the enrollment different? Right? So those are going to become our 3 main tests usually anyways. But yeah, this is our first look at doing hypothesis testing in Excel. Next class, we'll kind of look at proportions. I'll work through some confidence interval hypothesis testing for those, and then we'll look at how we do that in Excel. And we'll probably start on looking at examples where I've got sample means, but only sample variances. So on your way out here, stop the recording here real quick, because I'm just going to hand out